Good day and welcome back for the second part of our discussion on limits at infinity. As a reminder, in our previous video we discussed the concept of the limit of a function as you approach plus or minus infinity, and this is something that we can very clearly see graphically. As we approach infinity, say of 1 over x, the example we finished with previously, we're simply asking for a large and positive input. What are those function values or outputs getting close to? For the limit as x approaches minus infinity, you're asking the analogous question way off to the left. For large and negative inputs, what are those function outputs getting close to? So it's something we can very intuitively see from the graph of a function, or something we can maybe use in our next section to help us graph a function when paired with other bits of information such as intervals of increase, decrease, concavity, local maxes and mins, etc. So we're really working on being able to combine lots of good ideas together. And note in this case we would refer to the horizontal asymptote of this curve as being the line y equals 0. And note that as we discussed at the end of the previous video, there was nothing special with having 1 over x. In fact, for any positive quantity r, the limit as x approaches infinity or minus infinity of 1 over x to the r will also be equal to 0. And that will allow us to very conveniently and effectively evaluate limits as we approach plus or minus infinity of rational functions. Think a polynomial over a polynomial. And let me give you a little bit of intuition with this example. If we were to just think about what's happening individually in the top and the bottom, i.e. applying our limit laws that we previously discussed, there's a small issue. If you look at the top individually, it's going to infinity, and the bottom is individually going to infinity. Large inputs to either of these give you large outputs. But we don't really have any meaning associated with infinity over infinity. It is something we will try to handle when we get to calculus 2, but for now we need to algebraically manipulate this. And how we are going to go about algebraically manipulating this is we are going to multiply by 1 in a fancy way. I'm going to make the following observation. The largest power of x that we see in the denominator is 2. So I am going to multiply this by the quantity 1 over x squared divided by 1 over x squared. And this is going to be a general approach that we can use for limits of this form. And the idea here is as follows. Find the largest power of x in the denominator, and it is very important to emphasize that we're using the denominator to kind of guide us here in terms of what we are going to multiply by. Let's say that power is n. In our example above it was 2. And what we do with that n is we use it to multiply by 1 in a, I'll say fancy, or maybe you'd say a not so fancy way. And we multiply by 1 in the form 1 over x to the n divided by 1 over x to the n. So let's see why this is so useful. If we take that 1 over x squared, and we do need to let it go ahead and distribute through and hit each term in the top, each term in the bottom. So at this point it's purely algebraic manipulations. So in the top, when 1 over x squared hits the first term, we're left with a 2. The middle term, we're left with a 1 over x. And the last term in the top, a 2 over x squared. Similarly, when that 1 over x squared distributes through the bottom, we're left with 7 plus 2 over x minus 3 over x squared. And we are now in the scenario that we want to be in. That is to say, we can apply our limit laws. The limit laws tell us that we can take the limit of the top, divide it by the limit of the bottom. And in the top, you can go ahead and break that limit up into the limit of the first times the limit of the second, plus, and we'll even go ahead and pull that constant out in the limit of the third. Similarly, in the bottom, we're left with, once that limit is broken up, and constants are pulled out. And note, you could get here in multiple steps, but I am perfectly okay at this point in making that jump to the step. And note, each and every one of these limits are now things that we can, at this point, easily evaluate. From the new limit law that we've introduced, the last two limits in the top and the bottom all approach 0. They're of the form 1 over x or 1 over x squared. The first two limits are the limit of a constant. So what we have in the top is 2 minus 0 plus 2 times 0. And in the bottom, 7 plus 2 times 0 minus 3 times 0. That is 2/7. And I'd like to note that by comparison to this limit law that we have above, there's nothing special about taking the limit as x approaches infinity. The same exact calculations can be used to evaluate the limit as x approaches minus infinity. So similar calculations, just adding in enough minus signs, show that the limit as x approaches minus infinity of this function is also equal to 2/7. So I would like you to write down what is the horizontal asymptote of this function we've taken the limit of. So if we call this f of x, the horizontal asymptotes of that function f of x, remember, will be a line, y equals 2/7. So just to reiterate, 2/7 is not the horizontal asymptote, y equals 2/7 is the horizontal asymptote. Let me also emphasize and remind you that we should be using good, proper mathematical notation. So align our work vertically in a single column like we've done here. We show our limit at each step. We can clearly see how we've used the limit laws, and we write our equal signs. One other observation worth making, and hopefully something you remember from spending some time finding horizontal asymptotes of rational functions in your pre-calculus course, is that the 2/7 is something that we can actually identify. That's the leading coefficients of the top and the bottom. And it turns out that's not a coincidence, but in general, we have a property that we can use for calculating these infinite limits of rational functions that does not require us to go through this work. So if we have a rational function, remember that's a polynomial over a polynomial. And if the polynomial in the top has this form ax to the n plus some lower order terms, and q of x has the form bx to the m plus some lower order terms. So note it's going to be all about the degree in the top and the degree in the bottom. So a few kind of key facts. It has to be in this form a polynomial over a polynomial. We would say that the degree of the polynomial p of x is n, a positive whole number, and the degree of this polynomial q of x is m, another positive whole number. The value of this limit, think of it as a blank that we want to fill in, depends upon comparing the degree of the polynomials in the top and the bottom. How are m and n related to each other? And it turns out that there are precisely 3 cases. You could have m bigger than n, so that would be the degree in the bottom is larger than the top. You could have n larger than m, so the degree in the top is larger. Or like our example above, you could have the degree in the top and the bottom being exactly the same. And it turns out we can, with no work whatsoever, write down exactly the value of that corresponding limit. If m is bigger than n, that is the degree in the bottom is bigger than the top, you're dividing by big quantities, you're approaching 0. If the power is larger in the top than the bottom, your limit goes to infinity. And if they're equal, just like we saw above, you divide their leading coefficients. And just to finish by connecting this to our previous example, when we had the limit as x approaches infinity of 2x squared minus x plus 2, all over 7x squared plus 2x minus 3. Note immediately we can say degree 2 in the top, degree 2 in the bottom. So we simply divide their leading coefficients. And the value of this limit is 2/7. We will further explore examples in the next few videos, starting with this maybe less interesting case of having a rational function. And I say less interesting because we immediately get the value of that limit with essentially no work. And we'll build our way into some more interesting examples where we do not necessarily have a polynomial over a polynomial. So stay tuned and take care.